In this playlist, we're going to take a look at the fundamental theorem of calculus. Rather than actually doing the fundamental theorem of calculus directly, we're going to look at how you can utilize the fundamental theorem of calculus to do other problems. So this part of 5.4 is on using the fundamental theorem of calculus. The first use that we're going to see has to do with the area between curves. Imagine that I have two curves here. I have one which is here in red and one which is here in blue. And I want to find the area in between them, in this case from 4 to 8. So I want to find the area that I have shaded in red. If you think about this, the signed area of the red curve would be the red section plus the blue section, because the signed area of the red curve goes all the way down to the x-axis. In this situation, it's convenient because the red curve and the blue curve are both above the x-axis. So each area is positive. Therefore, if I were to find the signed area of this red curve, I would have found the area shaded in light red and in blue. Similarly, if you look at the signed area of the blue curve, it's simply the area here in blue. So if I want to find the red area alone, all I have to do is think, well, that's the signed area for the red curve minus the signed area for the blue curve. And we know signed area is given to us by definite integrals, and that can be found through the fundamental theorem of calculus. If the area between the two curves, if we're not always above the x-axis, but rather sometimes we're above and below, then the signed area will still be the top curve signed area minus the bottom curve. Because if we're below the x-axis, the signed area of the top curve is going to be negative, and the bottom curve is going to be negative, but it's going to be a larger negative, larger in terms of absolute value. So when I take the top curve area minus the bottom curve area, I still get a positive number. What we're saying is, regardless of whether or not we are above or below the x-axis, the signed area can always be found by taking the signed area of the top curve minus the signed area of the bottom curve. That's what this theorem here says. We want to find the area between curves f and g on the interval a comma b. This is a closed interval, a comma b. If we do that, we take the signed area between a and b of f minus the signed area between a and b of g. You can combine that into one integration, which says take the signed area of f minus g with respect to x. This formula here assumes that the f function is the one whose outputs are bigger. So f of x is the one that's on top. If we're in the midst of doing a problem, we always have to figure out which curve is on top and which one is on bottom. Again, this formula has notation where f is on top. If G would have happened to have been on top, then we would have switched and we would have said G minus F. This gives us a really nice way to find area between two curves. Let's do an example where we calculate such an area. We want to find the area between y equals x and y equals 6 minus x squared on the interval from 0 to 2. Y equals x, y equals 6 minus x squared. The interval is from 0 to 2. The first step that I should do is to figure out which one of these curves is on top along this interval. That means I want to graph both of these. Let's go ahead and do that. Y equals x and y equals 6 minus x squared between 0 and 2. Now, between 0 and 2 means x values are between 0 and 2. So we are zooming in on this region here. Let me shade that, noticing that the red is on bottom and the blue curve is on top. That's really all I need to figure out. So we take x less than y less than 6 minus x squared, and that is from 0 to 2. So we're trying to find this shaded area. Obviously, in this shaded area, like I said, the blue curve is on top. That's the 6 minus x squared. The red curve, y equals x, is on bottom. Once I know which curve is on top and which curve is on bottom, then I can set up my integration. I need to do a definite integral. So definite integral. Our bounds are clearly x bounds from 0 to 2. And then I'm going to integrate 6 minus x squared minus x with respect to x. At this point, what I would probably do is I would probably simplify this before I try to get an antiderivative. So combining like terms would give me negative x squared minus x plus 6. I combine like terms, obviously there was nothing to combine, and then put them in descending order. Now I use the fundamental theorem of calculus to actually get my answer. An antiderivative of negative x squared minus x plus 6 is negative 1/3 x to the third minus 1/2 x squared plus 6x plus a constant of 0. That's one antiderivative. It's not the only one. You could use any constant that you want, but 0 generally is the easiest. If you plug in a 2, what you'll get is negative 1/3 times 2 to the third minus 1/2 times 2 squared plus 6 times 2. And then if you plug in a 0, you would replace every x with a 0. When you replace every x with a 0, I hope that you see all of this stuff inside here just becomes 0. Sometimes you can save a little bit of work by just doing that. Go ahead and plug this number into your calculator. When I do that, I end up with the number 7 1/3, or 7.33. Oh, that was in there. So 7 1/3, which is approximately 7.33. This minus 0 isn't going to do anything. So there we are. That means that the area that I had seen shaded in green is 7 1/3 square units, whatever those units happen to be. That's how we find area between two curves. I'm going to show one more example. This says to find the area between y equals x plus 4 and y equals sine x on the interval from 0 to pi. The first thing we need to do is figure out what these things look like so we can figure out which one is on top and which one is on bottom between 0 and pi. So let's graph those. I've already graphed these two functions. You can see the y equals x plus 4 goes here. The y equals sine x is this wave down here. Between 0 and 4, well, the line, the straight line, is always above y equals sine x, between x values of 0 and 4. So I know the x plus 4 is going to be on top, and the sine x is going to be on bottom when I do my integration. Now we're going to set up our integration. What we do is we take, and we know we're doing the interval from 0 to pi. By the way, I think I've said this a number of times, but make sure that when you're dealing with trig functions like sine, you're in radian mode as your default. Because y equals x plus 4 is on top, I am going to start with that. Because sine of x is on bottom, I'm going to end with that. So we get integrating x minus 4 minus sine x with respect to x from 0 to pi. In terms of simplifying that, I tend to simplify before I try to apply the fundamental theorem of calculus, just because there's a lot of parentheses and things like that. Even though these two functions can't be combined, you can still write this as x plus 4 minus sine without the parentheses. If you would rather write it a different way or in a different order, that's okay too, as long as one term is x, another term is 4, and another term is minus sine. Let's go ahead and apply the fundamental theorem of calculus. We do that by finding an antiderivative, 1/2 x squared plus 4x plus cosine of x would be 1 antiderivative. It's not the only one, but you can do that. The x and the 4 get our usual polynomial treatment, and the antiderivative of sine is negative cosine. Therefore, negative of negative gives me a positive cosine when I integrate. I'm going to be plugging in pi and 0 into my antiderivative that I found. If I plug in pi, I end up with 1/2 times pi squared plus 4 times pi plus cosine of pi. I'll calculate that in a moment. Then next I would plug in 0, 1/2 times 0 squared plus 4 times 0 plus cosine of 0. You can either plug this in into your calculator in 2 steps, or you can do it in 1, or some people prefer, because this part of the function is coming from a polynomial, they will delete that part of a function because it's 0 and plug it in this way. By the way, cosine of 0 is not 0, so I can't get rid of cosine of 0. I can just get rid of the polynomial when I plug in 0. So you can do it that way as well, or you can just leave it as is. I'm going to type this entire thing into my calculator in 1 step. Now, because we're dealing with pi, we're going to probably end up with an irrational answer. And that's okay. We'll just approximate and round to 2 decimal places. Once I've calculated that, I get approximately 15.50. If I keep going in my decimals, it's 0.501178281 and probably goes on from there too. At this stage, I'm just going to round it to 2 decimal places, 15.50. So that's how to find area between 2 curves on a closed interval. We can utilize the fundamental theorem of calculus to do that. I would like you to try this problem. Find the area in between these 2 curves on the given interval. Push pause on the video, try it on your own, and then in the next video, I'll show you how it's done.